There's no running late. Once the class begins, ideally I should lock the door and even the TAs stay out, right? Who else is coming? So ping them both. Yeah, Paul is in Kigali, he should be online. Yeah. And ping Paul, tell him to be online on Zoom. Because he too can, release the Piazza pulse, right? Yeah, you're going to be doing that, but yeah, I know. But in principle, he too could do it. So we want the folks online to stay. He could be monitoring the questions on Piazza and such like. All right, folks, that's everybody. Your attention, please. Can we settle down? Hello, please shut your laptops. And why is the class so empty? Is there something going on today? Right. So we usually have this policy. We pick the days on which we will decide attendance. I'm not joking, right? So I can pick some arbitrary subset of three classes or 5, or maybe every last one of the 25, and decide their participation point based on that. So if you decide not to come and a bunch of your friends decide not to come on that day, I'm very likely to choose that date. Just to let you know, right? Shut your laptops, guys. Let's begin. It's 12:30. So, Josh, where did we leave off?
Last time we left off talking about how we could add like momentum and faster or get stuck.
So Josh reminds us that where we left off is where we were speaking about how we can add regularization or momentum. Momentum, we were not speaking of regularization, right? Momentum and second order methods to decide the learning rate to make things converge faster or slower. Now, so here's a quick recap. Here's where we are. We saw that we can train a network by minimizing a loss, which is the average divergence across your training samples, which is an approximation to the true risk, which is the expected divergence between the actual and desired outputs of the network. We minimize this loss through gradient descent, which is where we perform iterative updates against the gradient of the loss with respect to the parameters. Batch updates are what you're supposed to be performing. You want to compute the average over all of your training data. So can someone tell me, Lihan, why is batch the correct thing to do in principle? Somebody else, Omar?
So like maybe if we have a graph training sample instead of single one in the gradient descent, then we can have a more stable like gradient.
Well, that's an answer. So Omar, do you have an answer?
What was the question?
So why is batch update the correct thing to be doing?
Is what?
Why is it the correct thing to be doing?
Because it's taking into account all the samples at the same.
It's taking into account all the samples because why is that important, Rucha? Maybe somebody else? Yes.
Decreases the variance in the
It
estimate.
decreases the variance of your estimator. The average loss over all of your training samples is your proxy for the shaded area. Remember the overall expected divergence. You're just taking it over a bunch of samples. The larger the number of samples, the less sensitive you are to the specific set of samples that you chose. And so what is the largest set you can take? Everything, right? But then that's very expensive. So incremental update algorithms like SGD or mini batch speed it up by using random individual inputs or subsets of inputs for updates. And these are faster to converge, but they also have greater variance. And so there's a trade-off. Then we also saw the trend algorithms, which are the momentum and momentum-based methods and the second order derivative-based methods, smooth out variations in the incremental update methods by considering long-term trends in the gradients, which can lead to faster and better convergence. So more topics for the day. We're going to be looking at some of the issues of, some more issues that relate to generalization, how well the model learns, and why, under what conditions you can actually expect it to behave properly. The first thing, let's look at the loss, or the divergence, which is the loss for individual instances. So now the total training loss is the average divergence of over the entire training set. And the convergence of your gradient descent is going to depend on the properties of this divergence, right? So what was the ideal shape for this loss? Anyone remember? Convex. It has to be ideally something almost quadratic, right? A nice bowl. And why is quadratic better than, say, a cubic? If I took magnitude of x cubed, I claim that that's not as good as x squared. Why would that be? So that has to do with steepness. So when you plot x versus magnitude x raised to alpha for different alphas, for 1, it's going to be like this, right? For alpha equals 1. For alpha equals 2, so this is a problem. You have this corner, and so you have issues. For alpha equals 2, you get a nice, beautiful bowl. For alpha 3, what happens? It still is a bowl, but it's going to become something like this, right? As you raise the power, it gets flatter and flatter near the minimum. And so which means that your gradient descent algorithms will speed down the walls, but then as they approach the optimum, they're just going to slow down to nothing. So that's why we actually look at quadratics, because they have a nice kind of behavior. But anyways, the convergence of gradient descent depends on the divergence, right? It has to have the proper shape. So let's take a look at these different divergence functions. A good divergence function should not look like the figure to the left. You have no idea where you're going. Your gradient descent is going to end you, can take you anywhere, right? Now, I'm showing you 2 other gradient divergence functions. I'm claiming one of them is not so good and the other is better. So which of these 2 would you think is the better divergence or the better loss? The one to the right. Why?
Because you're more likely to be able to find the minimum, like the start of the slope that'll get you to the minimum quickly.
Yeah, there are 2 reasons, right? First, if you look at what would happen on the figure to the left, initially the function is very shallow. So at the beginning of the algorithm, your steps are going to be very small because the slope is very small. But then as you begin to approach the optimum, It becomes very steep, and no matter how small your learning rate, you're very likely to overshoot and begin bouncing around. So a function like the one in the middle is not a very nice function. What you want is a function like the one to the right, where as you approach the optimum, it becomes shallower, and so your steps are going to be more careful as you get to the optimum. So we've seen a few different options for divergence. The first one was the L2 divergence. What was the L2 divergence? It's the quadratic error between the target output and the actual output. So if the network output is Y, then if this is your network, you have an X and the output is Y, and then you have your desired output D, you can have the Y minus D whole squared. There's a half over here. You always have the half just for the sake of, for a reason that we'll see shortly, okay? So that is your divergence. Now, what will the shape of this figure be with this divergence be as a function of Y? It's quadratic. So can someone, it's going to be a parabola, right? So it's going to be, this is your D, and this is Y, and it's going to be a nice little bowl, okay? So this is a nice loss function. Now, the other loss function that we saw was the KL divergence. What was the shape of the KL divergence? Anyone remember? Think of the binary case where you have only, yeah.
It's again like kind of a parabola, but like it intersects the one point, right?
We went through this a bit. Anyone remember Ronak? What did it look like? Is it exactly a parabola? What was different about the KL divergence when compared to L2?
Minimum is not at 0.
It's minimum, well, the minimum is never at, the divergence is going to be 0, but
It went to infinity a lot faster at like one specific threshold.
and what else? So Ritu, you are nodding, so maybe you have the rest of the answer. The gradient is not 0 at the optimum, correct? So you had, for the KL divergence, you had the behavior like this. So if your target was 0, then, and this is Y, then the function would be something like that. This too has this nice property that it's very steep far away, and then it approaches the optimum very, very quickly. But this is in terms of it's quadratic. So both of these have the right shape in as functions of the output of the network, right? Does this mean that they will still have the right kind of shape with respect to the parameters of the network? So which of these two do you think is going to behave better with respect to the parameters of the network, if you had to take a guess? The first one? Square? Let's take a look, right? So I'm going to give you a very simple logistic function, a single perceptron. A single perceptron has, what's the nature? If I have a logistic function, I have a sigmoid of summation I wi xi. Let's skip the bias for now, right? The parameters are w. So y equals, this is what we say, right? If you have a logistic. Now, if I'd have these two different functions. This is the KL divergence. This is the L2 divergence. And you might have wondered, why do I use the KL and not the L2 in my training? And besides, the fact that it's very steep. If I plot these as a function of the W, not the Y, right? So this plot is a function of, so this plot over here, I have all of these inputs. I have the W's. They get summed. And then they go through a sigmoid. You get a Y, and then you get the target output D, and you compute a divergence, right? So if you plot the divergence with as a function of Y, the L2 looks like a bowl, the KL looks like this beautiful figure out here. But if I take a step back and I plot it as a function of these W's, what does it look like? This is what it looks like. So the figure to the left is your KL divergence. And is that the kind of shape we want? It's the first example, right? This looks like this guy, the one to the left. And the KL divergence is the one on the right. That actually has the shape that you want. And so when you begin looking at classification networks, the reason we choose the KL divergence, one big reason that we choose the KL divergence as opposed to L2 is that when you look at it as a function of the parameters of the output layer, we're still speaking only of the output layer. The KL divergence is a nice, beautiful ball. You're going to, if the rest of the network were frozen, you're guaranteed to get to the optimum. The L2 divergence, not so nice. Okay, we still don't know what happens further down, but this is a, this is a good enough reason to be choosing the one over the other. So L2 is not convex, whereas KL is convex. But both of them have a unique global minimum. So yeah.
I might be asking this question too early, but why do they have such a different behavior when we look at how they're influenced by function parameters instead of the output?
That's the nature of the function, right? So what happens is that if you look at the sigmoid has this logistic, it has a log function in it, correct? So if you were just taking at, if you just, let's look at what happens on the input. So we said the function is like so with respect to W. But then when I take a log, this guy gets compressed a lot less than these guys do because the log, right? And so the thing becomes a bowl as a function of the output. Now, on the other hand, if you're looking at the L2, at the KL, the log in the sigmoid and the exponentiation in the KL sort of cancel out, or rather the exponentiation, the two kind of cancel out. So you end up with a nice bowl-shaped function. It's just the nature of the property of the function. That's all.
Professor, is this different if we ditch the sigmoid activation and versus look at like a ReLU activation function?
For the output layer, if you're performing classification, you would not really be looking at it. You would not be using ReLUs. But if you did,
oh, you're right.
If you did, then yes, it would be very different. Firstly, you couldn't compute a KL because the output is not going to be capped at 1, right? But if you stayed within the 0, 1, you'd find that the L2 works better.
Thank you.
So, okay. Now, why did we have this half when I spoke of the L2 divergence? I said half of x y minus d whole squared, right? So this is why. Now, typically, you'd be using a neural network for one of two tasks. You might be performing a regression, or you might be performing classification. If you're performing regression, then what do? You have all of the inputs coming in. You have the x's, you have the w's. These things get summed, but then there is no activation further. When you're performing regression, the final activation function is just going to be a linear activation, which just passes data through, right? So this is your z value, and this is y, but y equals z for your regression example, right? And so the derivative, and then I have my d, and when I perform regression, you typically will use a y minus d whole squared, the L2 divergence. Now, what is the derivative of this term with respect to y? What is the derivative of this? Minus d? Why? It's just going to be minus of y minus d, right? Okay. Or I can write this as the other way is d minus y minus d. It's y minus d, right? So the derivative of this is going to be y minus d. I may have a sign off. What is the derivative of d with respect to z in this case? Come on, guys. Somebody say it aloud. Someone on Zoom. This is so simple. Okay. So Muno, what is the derivative with respect to z in this particular example?
Y minus d.
It's still going to be y minus d. Why? Because y equals z, right? There is a linear activation. This should not take so long. So for the next one, I will wait till someone gives me a proper answer. Okay. What do you expect? Now, in the case of classification, I'm going to have the same thing, x's, w's. You have a summation, you have a z, but now you have a sigmoid, and then you have a y. You have your desired output, but now this divergence, I'm going to say this is my Kullback-Leibler divergence, okay? So when I take the derivative of the KL divergence with respect to y, it's going to be something ugly, right? So what is the derivative of the KL divergence with respect to y? Actually, it's not even ugly. We saw that. Anybody remember? Minus? If the desired output was 1 hot, what was it? Come on, guys. I'm going to stop. I'll wait. If the desired output is 1, do you want this? What do you want the slope to be? Do you want y to be increasing or decreasing? So what do you think the derivative is going to be, positive or negative? Positive? So for the gradient descent, it's got to be negative, right? Okay. So this was it not something of the form of, what was the, okay, can someone at the back tell me the formula for the KL divergence? Sage, what was it like? I'll help you. Right? Now, we've written this several times. So what is the derivative of this KL divergence with respect to y? So, guys, this can't be so hard. The first term, minus 1 over y, that's all it was, right? Why was that so hard? Can someone tell me why you're getting lost? Okay. Now, that's a kind of ugly function, right? But then, if you take the derivative with respect to z, meaning taking a step back past the sigmoid activation all the way down to z, one step further, that actually ends up becoming y minus d. So the derivative for the classification network, where you have a softmax or a logistic activation at the output, the derivative of the KL divergence with respect to the affine term, pre-activation affine term, is simply the error between the output and the desired output. In the case of the L2, even there, if you are using a linear activation, the derivative of the L2 divergence with respect to the pre-activation Z is going to be the error. So, and of course, we are using a linear activation when we are performing regression and a softmax when you're performing classification. So in both cases, the derivative of the divergence with respect to the pre-activation affine value is just directly the error. So if someone were to ask you to pass derivatives through the softmax, you wouldn't bother working out the formula and doing a two-step process. You can simply say it's always going to be y minus d, right? So this is why this is called, this algorithm of passing the gradients backward was called error backpropagation, because at the output layer, just before the activation, the gradient is just the error. And that's what gets propagated backwards. And so the terminology, error backpropagation. Any have to pulse? Can you set a timer? 45 seconds, guys. I've been very slow. So I have good news for you. I'm not going to finish today's lecture on time. I will take an extra later in the night just to wrap up this subject. Can you get the poll? The poll numbers are up there, 376 and 377. Okay, 10 seconds, guys. Yeah. You should be able to find the poll. Everybody else is. That's poll number 370, post number 376 and post number 377. All right. So anyway, let's stop. Someone on Zoom, what's the answer to the first question?
AL.
Pardon me? Okay, both of you spoke. So maybe someone here can tell me? KL. What about the second one? For most popular networks, regression network with a linear final layer and L2 loss, or a classification network with softmax output and cross entropy loss, the gradient of the loss with respect to the final affine Z is going to be just A. It's always going to be the error, right? And so that's why coding this is so trivial. You wouldn't actually write ugly code. You just say Y minus D, you're done, because you ignore the final activation and go directly to the pre-activation term, okay? So story so far, gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. The choice of divergence is going to affect both how fast you learn your network and eventually also what you end up learning, right? And you have to be so you have to be careful about the divergence. Now we switch to another problem. We're working, let's assume you're working with mini batches, right? What is the assumption we had about mini batches when we trained?
That all the batches, their properties are similar, their mean standard deviation.
You're assuming that every, yeah, go ahead.
Randomness.
So your audio is a bit distorted, but the assumption that you're making that every mini batch has the statistical properties, gross statistical properties of the overall data itself, right? So you'd assume that if each of these colored patches was one mini batch, you'd assume all of them lie roughly in the same region of the space. That way you can operate on individual mini batches and you can converge really fast. In practice, what you're going to have is something like this. Every mini batch is going to be different. The mini batches are all going to have different distributions, and the differences can be very large. So in this case, optimizing for the yellow mini batch and taking a gradient step taken for the yellow mini batch is obviously completely inappropriate for the brown one, right? So we need to sort of somehow modify even our mini batch data so that they have the same gross statistical properties. So what you would want to do is sort of shift all of our mini batches. These are vectors. So the vectors can be scaled and moved by multiplying them component-wise by something and adding a bias term. And so you want to shift all of these mini batches to a standard location that represents the overall distribution of the data itself. But then what is that location? We have no idea. That too has to be guessed, right? So if we try to perform something of this kind, then you'd have to find the optimal shift for each mini batch individually, which is not going to be feasible. So what we will do instead is first move all the mini batches to origin. Every single mini batch is just going to end up at origin scale so that it has a standard variance and the mean is 0. And then from origin, there's a steady shift which will apply to every single mini batch, because once it's come to origin, they're all standardized. Then the mini batch can be shifted to the new location and the new scaling, the new scale. So this eliminates the shifts between mini batches. This is what we call the batch normalization. Every mini batch gets normalized. And so, yeah, this has you have only 30 seconds for this. All right, guys, 5 seconds. This is very easy. Yes?
How would you move all your mini batches to the origin?
Pardon me?
How would you move all your mini batches?
You're going to go through all of that in a bit, right? What was the answer to this question? Mini batches, thank you, right? So now batch normalization is a shift adjustment that happens, but we can apply it at different locations. This business of not standardizing mini batches, that holds valid because your data, as it passes through the network, gets moved around. So small differences between mini batches can become very large and get magnified when the mini batch gets passed through the network. So you would want to perform the standardization pretty much everywhere in the network, because the network has the property of sometimes magnifying small differences. And so what we would do is to have this batch normalization applied in various portions of the network. It would be an entire layer, sometimes after a layer. Now you can apply the batch normalization on the affine values just before the activation, or you can apply the batch normalization on the post-activation Y values. Both are equivalent, but I'm going to assume that we're doing it on the affine values just before activation, right? So how does batch normalization work? The mini batch, the first thing you want to do is, this is Ritvik, this was your question, right? How do you shift the batch to 0? Yeah, how would you do it? Yes.
You basically would calculate like the mean of the entire mini batch and then subtract it.
Exactly, right? You're going to find the mean of the mini batch and subtract it from everything, which means the entire collection is going to get shifted so that it's centered at 0, right? Then that's the first operation. The second operation is you want to normalize the spread. So for every single component, you would then find the standard deviation, which is shown by this second term over here. And so the actual normalization is going to be, you subtract the mean from the z value, and then you divide by the standard deviation. There's a plus epsilon just to prevent division by 0, right? Yeah.
Professor, I'm curious, like, I know that we basically have the assumption that we randomize the data so that the many batches are as distributed as possible. But with this sort of method, let's say that we're looking at like a credit score classifying deep neural network. If, let's say, one mini batch is for people with high incomes and one batch is for people with low incomes, just based on the distribution. Because we're doing normalization, don't we lose that like
You're
inherent?
predicting something that's coming later in class.
Okay. Sorry.
No, that's a good question, right? And that falls out of the math. That's beautiful. You'll actually see this, okay? So the first thing that happens is that you subtract the mean. This is at the scalar level. The z is being computed for every neuron, right? And so you'd subtract the mean and divide by the standard deviation. Is there a question? What is that? Can you read it out? You could apply it before or after. The whole point is the normalization. I'm just right now in the lecture, I have to pick my spot. I'm picking before activation, right? So, but then once the thing has been shifted to have 0 mean and unit standard deviation, then you move it to a new place, right? And then you scale it. So you scale it to have the distribution that you expect is natural at that point. So you wouldn't shift and scale. You would scale at the origin and then shift the whole thing to the new location. And so the modified data are going to be z hat, which is gamma times u plus beta. U is the standardized value, which is obtained by subtracting the mean and dividing the result by the standard deviation. So we're subtracting the mean out of the z and dividing by the standard deviation. And then this u is multiplied by gamma to get it to a standardized scale. And then it's shifted by beta to get to the correct location. So is this making sense to everybody, this process? Right? The why we are doing it and what we are doing must both be apparent, right? So you lady there, can you shut your laptop? It's disconcerting. Yes, thank you. Yeah.
I didn't get what's the point of after the standardization of the shifting.
So the assumption is that there's a natural, if you're trying to match the distribution of the overall data. Where is that centered? That's where you're trying to go. Yeah, yeah.
But during training time, we have many matches, but during testing time.
We will get there. It does cause a problem, right? So you are normalizing the mini batch to 0 mean unit variance, and then you're scaling and shifting to the right position. I can write the whole thing down, as a figure. If I had to plot it, this is what it's going to look like. I have the weighted sum of values coming in, as a bias. I'm ignoring the bias. You can imagine I have one more input, which is 1. And so I get the value z. And the z is now batch normalized, but it has a 2-step process. The first step is the first yellow box, where you bring it to origin and standardize. And the second step is the scaling and shifting, which is the second yellow equation. So, and then that resulting z hat is now going to be passed through the activation. Now, if you look at the math, if you look at the picture a little more closely, I can say that the second block is basically just this operation. The u that comes out gets scaled by some gamma, and then you get some beta added in, right? Questions? Anyone? You've been using this? Yeah. Yeah.
So how would we know where to shift it to exactly?
Yeah, so ask me after 20 minutes. Okay. So now there's a problem with this whole process, right? In conventional training, and it has to do with training. In conventional training, the mini batch loss is the average of the divergences between the actual and desired outputs for all the instances in the mini batch, right? So when I take a derivative with respect to any parameter, it's going to be the average of the derivatives of the losses for the individual instances. That's because so I can compute each of those individually, right? I can just pass each instance through, perform a backpropagation, and compute a derivative, and I'm happy. And I can do this for all of the instances in my mini batch and average these divergences. But then, if I'm performing batch normalization, can I still do this? Can I treat each input independently of every other input? Yes or no? How many of you think yes? No. Okay, why not?
Because it shift depends on other inputs as well.
Each input decides how the other guys get processed, right? Because they are looking at the mean of the mini batch. And so in batch norm, the outputs are now functions of the mean and the variance of the mini batch. And so if I were to write the output of the network, the output in response to any input is actually an output in response to the input, the mean of the mini batch, and the variance of the mini batch, right? So which means that all of the remaining instances influence mu and sigma. So I have to take that into consideration. So I can't just treat each instance individually. Now, how does that change my computation? So now the way to think about it is, remember, earlier we were speaking of scalar activations and vector activations. What was the difference between a scalar activation and a vector activation, Eli?
A vector activation has multiple inputs versus scalar.
Yeah, but there was something else. There was a little more to it than that, right? In a vector activation, you could assume that changing one input would change some other output. There wasn't a direct.
Oh, right. They all affect the.
Every input affects every output, right? So here at the batch level, that's what's happening. I have in the batch normalization block, I have a collection of z's going in, and I have a collection of z hats coming out. And modifying any z at the input is going to change all the z hats, right? And any perturbation of any z hat on the outside is going to be attributable to every single z on the input side, right? And this has to be accounted for. It's actually a vector function applied over all the inputs from the mini batch. And this has to be accounted for in the math. Now, so how do we work out this math, right? This looks horrible. So we're going to work this math out, and we're going to see it's not horrible. It's complicated looking, but that's simply because you have a lot of terms. But if you write down all the dependencies, remember I introduced something called an influence diagram. If you follow the influences properly, then this should be no effort at all. So let's take a look. Go away. Any questions, guys? Questions, anyone? No? Okay. So here's what the actual computation looks like, right? Within any mini batch, here is what happens. you have all of these z's, and every one of the z's contributes to the computation of the mean. Every one of the z's and the mean contributes to the computation of the variance, right? And the mean and the variance contribute to the computation of the z hat. So that is the influence diagram that we are seeing, right? And then once you have the z hat for the individual instances, the activation is just applied directly to the individual z hats, right? So actually, if you look closer, every one of these z's, so the z's are transformed first into the u's, which are the normalized version, right? And the u's are then scaled and shifted. So if you look at it carefully, the cross-instance interaction only occurs at the u level. It does not occur when you're converting from u to z hat, right? Because from the z's, you're getting the mean. From the z's and the mean, you're getting the variance. These two are used to standardize the data, which give you the u's. But once you got the individual u's, each u was individually multiplied, and then you had a bias added to it, right? So the actual influence diagram is going to look like this. This clear to everybody? Right. So once you draw this figure down, the math falls out so simply. So I claim. So when I'm performing backpropagation, I'm assuming that I've computed the derivative of the loss with respect to the output z hat, because that's what backpropagation would have given you, right? And so this is because z hat came out of the batch norm block, and backpropagation has given you derivatives all the way to the output of the batch norm block. Now, from those, I can compute the derivatives of the individual ui's one at a time, individually. There is no cross interaction, right? So let's see how that works out. Here was my formula again. I had my mean, which was the average of all the z's. The variance was the standard deviation, the variance of all the z's. The u was computed by subtracting the mean and dividing by the standard deviation. And then the z hat was computed by multiplying that u by a gamma and adding a beta. So when I'm performing backpropagation, the derivatives would have come here. They would have gone past the activation. And then you're going to get the derivative with respect to z hat, right? So from the derivative with respect to z hat, now I want to compute the derivative with respect to u. That's easy. I have z hat equals gamma u plus beta. Now you guys help me, don't look at the board. So if I have dl over dz hat, then what is dl over du? Anyone? Gamma times dl over dz hat, right? So this is easy. But then there are these parameters. Multiple of you ask me, how do I know how much to scale it by, and how do I know where to shift it? Those are the gamma and beta terms. They can be learned, right? What is dl over d gamma? What is dl over d gamma? Again, don't look at the answer. I have dl over dz hat, right? What is dl over d gamma? It's going to be ui times dl over dz hat. And what is dl over d beta? It's just going to be dl over dz hat. And so we know how to compute these derivatives. So we can learn it. Once you know how to compute derivatives, gradient descent, you can learn it, right? You also know how to compute the derivatives with respect to u. And so at this point, we have worked our way back, and we have the derivatives with respect to the u. Everyone with me so far? So we've got the derivatives going backward all the way to u. And there was really no challenge in this. The real challenge is now figuring out how to compute the derivative with respect to the z's that went in, given the derivatives that you had with respect to u, right? For this, let's take a look at, okay, first answer a couple of questions. Perfect. Did it beep? Okay, here's the beep. Time's up, guys. What's the answer to the first one? Is the first statement true? Yes. Second one? Okay, and in the second question? True. Okay, so only the first statement was true, the second one was false, right? Because the normalized u hat depends on, for any zi, depends on all the other u's. The u's don't depend on each other, the u's depend on the z's, right? There's no direct dependence, okay? Yes?
So there's a single gamma and beta for a single layer, right? For
So
single point.
at any particular neuron, it's going to have its own gamma and beta. Yeah. Yes?
Isn't like considering we're finding the derivatives compared to gamma and beta, then aren't the u's like sort of like aren't the gammas dependent on the u? Like
Yeah. So yes, so you will have that indeterminacy, but in the end, the gamma times u will be the right value, right? That's all that matters. So now, but that's a good question. Now let's go back and see how I can pass the derivatives from the u to the z. Okay, this is complicated or looks complicated, and it's made complicated by the mu and the sigma, right? Sigma squared. So let me now. I know that if I want to compute the derivative with respect to any single z, every z influences all the u's. All the u's influence the loss. So I have to be summing over all of the u's, and I'd have to compute, then the term I'd be summing is the derivative of the loss with respect to u times the derivative of u with respect to the z, right? Now, for any z, there are two kinds of u's. There's the one that's in direct correspondence, right? Each z gets normalized to a corresponding u, but then each z also influences the other u's, right? So there's the through u, and there are the cross u's, right? So let's just take a look at the derivative for just this d loss over du we've said is already computed. This has to be computed for every ij pair. So you need to compute the derivative of every one of these u's with respect to each z. So for each z, you're going to get a whole bunch of a batch-sized number of du over dz's. And one of them will be the direct correspondence version. The rest of them are going to be the cross terms, right? So let's consider the direct correspondence. What is the derivative of the normalized u with respect to the corresponding z? Okay, so to see that, let's see, what does it look like? There is this link, right? So this means that you basically remember, what does the derivative compute? How do the perturbations of the inputs perturb the output? The u is perturbed in multiple ways. So the first perturbation comes through the through line, right? So that one is going to be the partial of u over z. Now this is where you will see that if there are multiple links going into the same thing, the definition of a partial kind of breaks down. So I'll just call it the derivative, okay? So this is the derivative of u with respect to z. So that's one thing. If I perturb u, it directly influences, z directly influences u. But then here's the second thing. If I perturb a z, it influences the mean. The mean and the perturbation of the mean then influences the u. So I'm going to need a du over dz times du over d mean times d mean over dz. Correct? Everybody with me? Yes. Now, there's another term, which is that? The variance, right? So if I perturb z, it perturbs the mean, it directly perturbs the variance, and then also perturbs the variance through the mean. Correct? And the perturbation of the variance perturbs you. So if I had to write it down, I'm going to have the derivative of u with respect to the variance times the derivative of the variance with respect to the z, but the derivative of the variance with respect to z itself is going to be a complex term, as you can make out by simply looking at the influence diagram. Make sense to everybody, right? So you can see how we are working this out. Once you draw the picture, the whole thing kind of breaks down and becomes very simple. right? So now let's try to compute all of these one at a time, okay? Let's take a look at the first guy. Yeah, this one, the derivative of u with respect to z. Now for the derivative of u with respect to z, you're speaking of the through line, right? So on this through line, the dependence between u and z is given by this formula, right? What is the derivative of u with respect to z going to be? Just the denominator, right? That's going to be 1 over sigma squared, square root of sigma squared plus epsilon. So I can just drop it there, right? Everyone with me? Now let's take a look at this one. You're still at this equation. What is the derivative of u with respect to mu? Minus, right? That's minus 1 over the denominator. And so let me drop that in there. Now, what is the third one? What is the derivative of the mean with respect to z? That's obviously going to come from this term, right? 1 over? Lovely. You guys are working this math out, right? You don't need me. Okay. So what do we have remaining? First, what is this guy? What is it's if you think of sigma squared as your variable, it's that variable raised to minus half, right? So when you take the derivative, it's going to be that it's minus half times the variable raised to minus 3 over 2. So that's going to be this, correct? So everyone with me, where this came out from? So let me plug that in there. Things are working out nicely, right? And then there's one more term. What is this? This is where it gets a little tricky, because the derivative of z with sigma squared with respect to z has two paths coming in. You would have to consider both, right? But let's work it out. What is this first term? What is on the direct path, the red path? Look at the formula over there again. What is the derivative of sigma squared with respect to zi? That's going to be sigma squared is the variable, right? So what is the derivative of this guy with respect to any particular zi? That's going to be 2 times z minus b over minus mu over b, correct? Everyone with me? So I can drop that in. And now, what is the derivative of sigma squared with respect to mu? So it turns out that this derivative is going to be 0. Okay, let's see why this is the case. Sigma squared, this mu occurs in every single summation term, right? The mu is constant. So if I take the derivative, it's going to be 1 over b, then I'm summing over everything minus 2 times z minus mu b, correct? What is that? What is the summation of? It is 1 over b summation z minus mu, where mu itself is 1 over b summation z. What is this going to be? It's the average of the centered data, correct? What is the average of the centered data? 0. That term 0, right? That goes away. Do I have to waste any time computing this guy? Okay, so that's that, right? And so here you end up with this equation. Is it so ugly now? Come on, guys. It was simple, right? We got it. We know exactly how to compute it step by step by step. If I left you alone in a desert with only a pen and paper, not even a pen and paper, just sand and your finger, you can still come up with a formula. So it's not so hard. So making sense? This is the formula that we will be using to compute the derivative, but this is only for the through variable, right? How perturbing a z influences the corresponding u. You want to do the same arithmetic for the cross term as well. So for the cross term, this is the derivative for the through line. For the cross term, I want to look at this guy, right? And for this guy, it turns out I only have this one dependency, derivative of u with respect to mu times derivative of mu with respect to z. and this term, derivative of u with respect to sigma squared times derivative of sigma squared with respect to z. Okay, and this is similar to the I equals j without the through term. And I won't work it out. This is what the formula is going to be. I trust that all of you guys can sit down with pen and paper and work it out. It's not so complicated. Or, finger in desert sand, yes.
Can you compute this beforehand and like use some parts of it for the actual?
The point is this is actually a function of the z's, so you can't really, you could compute it during the forward pass or something, I suppose, but it still needs to be computed, right? So now, here's what you've got. The derivative of u with respect to z, the derivative of any uj with respect to zi is going to be given by this two-part formula. When j equals I, you get this through formula, right? This is the j equals I term. This is what we derived. When j is not equal to I, it's the one at the bottom. If you go back and read the paper, it's not going to be very obvious where the formula came from, so it becomes religious belief at that point, but it's not religion, it's math. Right? So now let's take a look at how this thing behaves, okay? Now, the complete derivative, this is for a single instance, the derivative of each of the u's with respect to each of the z's for a single instance. But then if I want to compute the derivative of the loss, mini batch loss with respect to any particular zi, I'm going to have to sum over all the u's, right? Even for that single instance. And so it's going to be the sum over all of these j's of the derivative of the loss with respect to uj times the derivative of the uj with respect to zi. Okay. And things get tricky. So I forget your name. What's your name?
Dennis.
Dennis. Oh yeah, you're Dennis, yes. So you had a nice question. If I have these two batches which are pure, won't this kill them, right? Let's see how that works out. I'm actually going to write out the math for this. If I write out this entire formula, the derivative of the loss with respect to any given zi, that's going to be this guy here, right? Now, which is going to be the summation. So this first term, this for any particular zi, this first term is unique because there's only one through term, correct? Yeah. So that's going to stay. It's d loss over dui times 1 over sigma square root of sigma squared. The remaining two terms are going to be summed over the rest of the mini batch, right? And so the second term is going to be 1 over, actually it's going to be summed over the entire mini batch. So it's 1 over b sigma squared, square root of sigma squared, that was constant for all of these. Then you're summing over all terms, d loss over duj times, yeah, that's for the second term, this one, right? 1 over b times square root of sigma squared, and the summation of the loss with respect to uj for the entire term. Now the third term is going to be, I can write the sum jointly in this kind of complicated manner. The zi minus mu b is common to both, so I pull it out and write this, and the denominator is common. And the summation is going to be d loss over duj times zj minus mu b. So at this point, you have to trust the formula, but if you work it out, it's going to be, fairly straightforward, nothing complicated. And then once you compute that, you get the derivative with respect to the loss, and that goes back, right? That can be back propagated. But then, wait a minute, I have some, give me a second, I think I'm lost, okay. So before that, let me go back and take a look at the behavior of this one, right? Suppose I have a mini batch, and suppose all the instances in the mini batch are identical. So my mini batch is completely identical, right? What would that mean? Yes?
Is the right-hand side term going to be 0 basically because z of I is going to be equal to the mean?
This guy is going to become 0. Wait, so
yeah,
this last term is going to become 0.
Yeah.
Okay. What about this term?
Well, the variance would be 0.
So no, but it's even there's a plus epsilon. So the variance, right? What happens is d loss over du is going to be constant for all of these, correct? So this is simply going to be b times d loss over du. That b and this b will cancel. It's simply going to become d loss over du times 1 over square root of sigma squared, right? Which is the same, which is the negation of the first term. The two will cancel out, right? So if all the terms in your mini batch are direct, are constant, or are the same, or even very similar, what do you think is happening to the derivative? The derivative is simply going to become 0. Dennis, does that answer your question?
So if all of them are the same, the derivative becomes 0?
Yes. That's what the math tells you, right? You just explained it to me.
Yeah.
Right. And so this means that your mini batch must have diversity. If your mini batch does not have diversity, derivatives are going to get blocked at the batch normalization layer. They are not moving back further because the derivative becomes 0. And then subsequently, there is no information going backwards to compute derivatives. That makes sense? So this is a requirement of the nature, what the mini batches must themselves look like. You can't have a mini batch which is all one class. If you do, that mini batch you might as well throw it away because it's passing no derivatives backwards. You cannot have a mini batch where all the instances are very similar. It's going to not pass very much of a derivative backwards. Yes.
Is that something we should enforce on our data, or does that come out of random selection most of the time?
Yeah, it should come out of random selection most of the time, but it might be, if you find things getting stuck, it might be because of this. Yes.
Does that problem only occur if you normalize, or if you were to use mini batches?
If you use batch norm, then the derivatives are going to get killed. That's it.
Okay.
Right?
The problem in the forward pass as well.
Meaning?
Even in the forward pass, that time
I mean, if I have a very small difference, because you're going to be scaling by the variance, right? If it's a minor perturbation, it will look magnified going forward. But going backward, you're still going to get killed. Right? Imagine a lot of instances which are just off by a little epsilon. The standardization by the standard deviation is going to make them look just fine going forward. But going backwards, your derivative is going to disappear. Right? So not quite. That's a different problem. Any questions? Yeah.
In like similar to what he said, like whether it comes out from randomization, like how would you, I guess, identify if like something like this happening for like some batches?
It's very hard for you to actually check this, right? So it's going to be impossible because it's a complex thing. But this is a test that you can actually check. You can take precautions. You can't have all your class 1 data going in first and class 2 data going in next. That's guaranteed to kill you, right? You want to mix the classes and mix the data. These are minimal precautions that you can take. And then if things get stuck, here's something that you can check. Okay. So all right, guys, can you shut your laptops, please? Again, remember, when I ask you to shut your laptops, I really mean shut your laptops. All right. Can you shut your laptop at the back? Thank you. This is not like a one-time thing where you shut your laptop at the start of class and then go back to Facebook. That's not acceptable, right? So here's your poll. Now you may open your laptops with my permission. Just 15 seconds for this one. This is easy.
It takes Piazza to load 15 seconds.
Sorry.
I swear to God. I lost so many polls because I was waiting for CMU secure Piazza to come.
Oh, good God. All right, so I think we're out of time. What is the answer?
True.
True, thank you, right? That's easy. And so there was another question. Who was it who asked, what would you do during test time, right? If you're at test time, was it you? So what would you do? You know how the process works, right? What would you do?
So now if we have gamma and mu learned.
Gamma and mu are already learned. So what are the problem? What is the problem here?
That we are only passing a single instance
So
rather than a batch.
if you were passing an entire batch in, then you could still estimate the mini batch mean and the variance and perform batch normalization with the mini batch mean and variance going forward, right? But more realistically, possibly only passing in one instance at a time. So what mean and what variance would you actually use? So in that case, here is what we do. You would compute the average of the means of all of the mini batches that you had in training. Once the model is trained, you're going to go through your entire data. And for every mini batch, you'd have a mean and you'd have a variance, right? You'd compute the average of the means and the average of the variances. You use what is called an unbiased estimator. That little detail is not a big deal. But the point is you're computing the average of the variance of all of your variances over all the mini batches and average of the means of all of the means in all the mini batches. And this is what you would use in your final inference. Okay. You may not want to actually go back through your data and do it all. So in practice, what we'll do is we'll maintain a running average of the means. And that's going to be our final mean. Similarly, we'd use a running average of the second moment of the variance, and that's going to be the final variance. Now, and batch norm, of course, may be applied only to some layers or some selected neurons in the layer. This is a matter of choice. But here is the thing you want to remember. The reason you want to keep applying this throughout the network and not just at the input is because the neural network is a very complicated nonlinear function. So as data go through the function, two data instances which are this close at the input can become that far apart a couple of layers down. And so you need to be aware that because of this drifting and separate and things which are far apart can come close together, all kinds of things can happen. So batch norm really is applicable at every position in the network. Yes.
About the running average thing, so do we maintain the running average at each layer across epochs, across mini batches?
No, in the final epoch only. Yeah.
Can you use the same technique to do online learning visualization?
Online?
Online learning.
You can have online versions of the same algorithm, right? Of course, during inference, during training the mini batch, you have the entire mini batch. There's no such thing as online. So the actual mean and variance values that you use, those are running averages. That's essentially an online estimate. Any other questions? No. Yeah.
How much, like, computationally does batch norm cost relative to, like, softmax or something?
So TAs, can you tell them? That's why I have these guys. How much does batch norm cost computationally?
Not much.
That's you got the answer, right? They are my experts. But how exactly does it affect training? This is this original paper by Sergeyov and Zagri that's in 2015. So the lowest dotted curve, this is for a complicated neural network for image recognition. That's how the model converges with iterations. And then the rest of the curves are the performance that you get when you apply batch norm. And you see that the model converges much faster and actually converges to a better optimum. So this is the kind of behavior typically expect with batch norm. It can make a difference between a functioning network and a useless network. On the other hand, a badly applied batch norm can make a difference between a functioning network and a useless network too. But the other way, yeah.
On the previous slide, you mentioned that you don't need to apply it for every layer. So how do you make the decision when to apply it?
That's a heuristic, right? So this is that's why we teach you how to run operations on your model and try various things, because you don't really know how the network is functioning. If you have a layer where the surface is largely undistorted, then when data go through that particular layer, the next layer probably doesn't need batch norm, right? Yeah.
Also, for every time we apply through the network, we are learning a different gamma and beta.
Yeah, this is going to be for every location where batch norm is applied, you'd have its own gamma and beta. Right. Okay. So the story so far, that we saw that the choice of divergence affects both the learned network and results, and the shifts between training and test may cause problems and maybe, or even across many batches, may cause problems and may be handled using batch normalization. So I've told you a lot about, how the models, how to train the model, and that we're actually using data as proxy, and that we're going to actually, this business of using a proxy helps us sort of estimate the overall loss function. I drew some very nice helpful figures. Those figures are kind of fake. So how are they fake? We attempt to learn an entire function from just a few snapshots of it, right? So this is the kind of picture I've been drawing all along. And we said that we define a divergence between the actual output of the network and the desired output of the network. So if you have some current setting of the network, it's going to compute some other function. And so at each of these points, you'd compute the error and you try to minimize the overall length, L2, whatever. There's no guarantee that it's actually going to learn the correct function everywhere, right? You might actually, so the blue dotted line might be just what you want to learn. Instead, you might end up learning the red curve. It nails all of your training points, but it's completely rubbish. This is not what you want. So how do we deal with this? You need additional smoothing constraints that will fill in the missing regions acceptably. In other words, you need to do something about generalization. So to explain how this works, one of the ways in which this works, consider a simple binary classifier. So if you have a binary classifier and you have one-dimensional input, the actual function that you want to learn is the blue curve, right? But as we know, the neural network is a universal approximator. It can learn anything. It could also end up learning the purple function. Which of these two would you think is the better one? The blue one, right? But which of them has the lower error? The purple one, right? So how do you prevent the model from learning this guy instead of the blue one? If the model is unconstrained, if the training is unconstrained, it's very likely to end up learning this unnecessarily detailed, ugly function and not learn the one that you actually wanted to learn. So let's look at why it can learn these things. In order to learn this function, the function has to increase steeply and then fall steeply and then increase steeply and then fall steeply, right? That's what it needs to do. And the perceptrons, in a case of, imagine I'm using a sigmoid activation, right? You have sigmoid of some w times x. If w is infinity, what is that function? It's a threshold activation, right? By allowing w to increase arbitrarily, I can make the activations rise and fall as fast as you want, as they want to. And that means they can end up learning this function. So what we would find if you were learning, and this I'm using the sigmoid as an example, but this is true of all of the activation functions that you will use. So if I use a sigmoid activation, as the magnitude of w increases, the response becomes steeper and steeper. And so in the limit, if I just want to learn that function and I throw the network at it and say learn, it's going to make all of the w's really large, and it's going to learn this hideous function, which is perfect on your training data, but not so good, not what you want. So what would you do? What does the regularization do?
Constrains the parameters would increase.
So you constrain the weights to be low and say the w cannot become too large. So when you do that, then you're forcing it to learn the blue curve rather than the very steep red one. And so in that case, you're going to actually end up learning a smooth function as opposed to something that bounces around crazily. So the way you would do it, in your conventional training, your loss is a function of all the network parameters, which is just the average of the divergences for all of the instances in your mini batch. And that's what you would be minimizing, right? Instead, now you're going to add a second term to this and say, I not only want my loss to be small, at the same time, I want to keep the weights small as well. And so you add this extra term to the objective, that lambda on the outside is the importance that you're assigning to keeping the weight small. If lambda becomes 0, you're going to learn this crazy thing. If lambda becomes very large, you're basically going to end up learning nothing because you'll just force the weights to go to 0. So there's some optimal setting of lambda that you typically have to figure out. But solving this gives you the the modified training, which gives you the constraint that we spoke of. So anyway, Isha, can you shut the laptop? Or you can go out. Okay. So, and how does that modify the derivative? The derivative is, in your standard loss, the derivative was just the average of the gradients for the individual instances. But then the derivative of the second norm, the squared norm of the parameters is simply the norm itself, right? That's why we have the half outside. So basically, you're going to say that to my gradient, I'm just adding lambda times w, transpose, because it has to be transposed for derivative. And this lambda times w is going to be applied to every single, to the loss, regardless of whether you're performing stochastic gradient descent, mini batch descent, or batch updates. And so this is cool, very simple. All you do is that lambda times the current parameter keeps getting added to the derivative each time. But when you actually implemented this in your homework, you sort of saw things slightly differently, right? This was not what you saw. So how are the two related? I'll see if I have the slides. The update rule is going to be just, this modified derivative, right? Here you'd use the modified derivative. If you look at that, for every layer, the new update, this is just the earlier one, the usual batch, mini batch update. The update rule says that to each W, you adjust it by minus of eta times, that is your step size times, the gradient plus lambda times W. Correct? So can you reorder those terms? You could potentially reorder them, right? So I can rewrite this instead as, instead of saying W minus eta times the gradient W loss of W plus lambda eta, this guy can come out here and it can become 1 minus eta lambda times W minus eta gradient loss, right? So in other words, this is the same as taking the current parameter, shrinking it by some amount, and then using the standard gradient descent update. So this is what you call isn't this what you guys implemented in your homeworks, right? You called it the weight decay. The weight decay was simply L2 regularization. Make sense? Right? Okay. So there's one final thing I'll try to cover in 5 minutes, and the other is this. There's another way of applying smoothness constraints, and this can be imposed through network structure. And for a given number of parameters, rearranging the network to be deeper rather than wider is going to give you smoother network functions. Why is that? Each function, so you start off with some flat surface, right? Or you start off with some ugly surface, and the data is scattered any odd how. And then each layer is going to sort of reshape the data. But each layer operates on the output of the previous layer. So if you have some layer that magnifies all small changes to make the differences really large, the next layer is going to see a very jagged landscape. On the other hand, if you have layers which sort of tamp things down, the next layer is going to see something that's damped down. And typically, you're going to have regularization everywhere. So each layer is now going to be operating on the output of the previous layer. And so when you have the layers which are stacked up many layers deep, having more layers means that the final output is going to be smoother than if you had fewer layers, because each of them is just operating on an already smoothed out layer. And so here are some examples of how that works. This is a couple of toy examples that we worked with. The black and white pictures are the decision boundaries that we are trying to learn. And in both these cases, we've actually used a neural network which has the appropriate architecture. These are just polytopes, right? Polygons. So we have a neural network with the exact right architecture for these decision boundaries. Then you draw a sample of like 1,000 points from those boundaries, and you train the network. The actual decision boundaries it learns are the nonsense that you see to the right. So firstly, the problem here is that I've taken the optimal, the minimal neural network for this problem. And it turns out that when you have a network that has just the right capacity, but when you try to learn it, it's very, very hard to learn. So you really want to have more capacity than than needed if you want to learn the function properly. But even with that greater capacity, how do you deal with things? So you have a couple of different decision boundaries over here. One of that looks like the hexagonal bolt on the left. The one to the right looks like a bear. And in each case, we've tried to, we've drawn 1,000 samples and tried to learn a network with 660 neurons, right? So if you set the 660 neurons as 3 layers of 220 neurons, you learn the decision boundary to the top left in the 2 panels. On the other hand, if I set it as 4 layers of 115 neurons, you see that it's changed a little bit. If I make it 6 layers of 110 neurons, it begins to look like the bolt. If I make it 11 layers of 60 neurons each, it gets something that looks like the bear end or the bolt. So it's the same number of neurons in every case, but just rearranging them to be deep versus shallow and broad gives you greater smoothness, and so you get greater regularization, so you actually end up learning the function better.
Professor, I'm curious, is like the more smoother thing that we see due to the loss like gradient being a lot smoother and it's being a lot easier for us to train it? Or is it just by the virtue of with deeper layers, we can articulate much more complex functions?
So with deeper layers, it also has to do with the fact that each layer is going to sort of restrict how much yeah, that's right. And so data under specification can result in overfitted models and must be handled by regularization and more constrained network architectures. So I'll stop here. I'm out of time, but I will take an additional half hour because I have something like 20 slides left or 30 slides left. I'll post a note about it, and that will be the final lecture in this series on training. Next week, we begin with convolutional neural networks. Okay.